Hello everyone. In this presentation, I am going to talk about a style-based generator architecture for generative adversarial network, or in short, StyleGAN. This is relatively a new concept in machine learning. StyleGAN is based on the GAN architecture, which was first introduced in 2014. And the goal of this was to generate artificial images which are not distinguishable from the real one. Let's first get introduced to the paper and the authors. The paper was first published at the IEEE conference on computer vision in 2019. It has over 5,000 citations till now, and all the authors work at NVIDIA. The main contribution of this paper is that it proposes a new generator architecture for GAN, which can generate high-quality images called StyleGAN. It leads to an automatically learned unsupervised separation of high-level attributes known as latent space disentanglement. It also proposes two new automated matrices for quantifying disentanglement and introduced us to a high-quality dataset of human faces. We will see more details about the contributions in the later slides. By now, we all know that GAN has two basic components, the generator and the discriminator. The task of the generator is to generate some noisy output images from some random input noise. The discriminator takes samples from both the generator-generated images and the real images from the training set and then predicts if they are real or fake. By comparing real and fake images, the discriminator improves over time. The generator also improves by receiving feedback from the discriminator to generate more realistic fake images. GAN images have become more realistic over time, but the problem with GAN is that it is hard to generate high quality images. It still operates as a black box, and we don't have any clear idea about the origin of the stochastic features to generate the synthesized images. It is also not easy to understand the properties of latent space. To eliminate the problem with GAN, NVIDIA proposed ProGAN or progressive GAN. The key idea of ProGAN is to start by learning features from low resolution images such as 4x4 and learn more and more about the features as the resolution of the images increases every time. The training process with ProGAN is usually faster and easier as it starts with low resolution images. Here, as the features are entangled with each other, it is difficult to tweak the input. If we try to do so in one feature, it will affect multiple features at the same time. StyleGAN is the upgraded version of ProGAN's image generator, which only focuses on the generator network. The author considered the benefit of the ProGAN progressive layers. It is possible to control different visual features of the images. The lower the layer, the coarser the features are affected. The paper divided the features into three categories. Coarse features, which affects the pose, face shape, identity, etc. Middle affects the freckles, hairstyle, eye open or close, and fine deal with the color schemes, such as hair color, eye color, or skin color. In the StyleGAN architecture, the traditional generator gets the latent code from the input layer. The output maps the input to an intermediate latent space W. The goal of the mapping network is to encode the input vector into an intermediate vector whose different elements control different visual features. But the model still need to follow the probability density of the training data. This means if the image of people with black hair is more common in the dataset, then more input values will be mapped to that feature. This event is called feature entanglement. To solve the issue, another neural network is used. Now the model can generate a vector that doesn't have to follow the training data distribution. It can reduce the correlation between the features by using adaptive instance normalization at each convolutional layer. Adaptive instance normalization, or in short ADIN, transfers the encoded information W from the mapping network into the generated image. The module is added to each resolution level of the network and defines the visual expression. Here, each channel of the convolutional layer output is first normalized to make sure the scaling and shifting has the expected effect. The intermediate vector W is transformed using another fully connected layer marked as A here into a scale and bias for each channel. The scale and bias vectors shifts each channel of the convolutional output, which defines the importance of each filter of the convolutional layer. Most of the models, including ProGAN, uses random input to create the initial images of the generator. However, the StyleGAN image features are controlled by mapping network W and the adaptive instance normalization. So the initial input can be omitted and replaced by constant values. This paper didn't explain why it improves the performance, but it can be assumed that as it reduces feature entanglement, it is easier for the network to learn. One of the challenges in generative models is dealing with the areas that are poorly represented in the training data, because the generator is not able to learn them and create images that resemble them. To avoid generating poor images, StyleGAN truncates the intermediate vector W by forcing it to stay close to the average intermediate vector. This is produced by selecting many random inputs. In fact, the mapping network transforms into W new, where the value of psi defines how far the image can be from the average image. For training data, the model randomly selects two input vectors such as A and B and generates the intermediate vector W for them. Then it trains some of the levels with the first and switches randomly to the other to train the rest of the levels. The random switch ensures that the network won't learn and rely on the correlation between levels. If we notice in the figure, we will notice that the first row here is actually getting the course style from B and mixing it up with the source A. Similarly, in the second row, it is taking a different hairstyle and freckles, and here in the last row, we can notice that we only get the fine style that is different hair color and face color. Nothing else is changed much here. So what about the variation that doesn't require mixing two different images? That is, what about we don't necessarily want this style from this image and that style from another image? We want to see the differences with the images we generated. So StyleGAN has that too, which is adding additional noise to the model, but which will add stochastic variation to the image. So here in the first half of the image is just injecting random noise into the fine layer. This gets the person to have much smaller curls of hair and the eyebrows are wispier, versus injecting noise in the coarse layer, which is in the second half of the image, gives us more variation in the coarse layer, such as here we get the larger curls and smoother eyebrows. This figure shows another example of stochastic variation. If we zoom in on the generated images, we will notice that the placement of individual hairs is placed very differently while the overall appearances is almost the same. The dataset consists of 70,000 images of very high resolution images. These images are also of very high quality and offer a lot of variations in terms of age, image background, ethnicity, lighting condition, and different viewpoints. The experiment was compared using the FID score of the Celeb HQ dataset and the Freckle Faces HQ dataset. The chart here shows the FID scores of different configurations of the model. The FID score is a score used to benchmark generative adversarial networks. The lower the FID score, the better the model is. They found that the more they added the novel designs to the baseline GAN architecture, the better the FID score is. This experiment also demonstrated that the FFHQ dataset achieved a better FID score compared to the Celeb BID HQ dataset. This experiment shows that the FFHQ dataset was better than the Celeb AHQ dataset. The paper also presents its results in two other datasets of bedroom images and car images. To present the qualitative measure of feature separation, the paper presents two novel ways to measure the feature disentanglement: the perceptual path length and linearly separability. The perceptual path length measures the difference between two consecutive images, where the which defines that drastic change means that multiple features have changed together and they might be entangled. Linear separability is the ability to classify the inputs into binary classes, such as male and female. The better the classification, the more separable the features are. By comparing those matrices for the input vector Z and the intermediate vector W, the authors shows that the features in W are more significantly separable. StyleGAN is the groundbreaking paper that not only produces high quality and realistic images but also allows superior control and understanding of the generated images, making it more even easier than before to generate believable fake images. The techniques presented in StyleGAN, especially the mapping network and the adaptive normalization uh, add-in, which will likely be the basics of many future innovation in GANs. These are all of the references used for this presentation. Thank you.